Hello, hello, hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see a problem. Sum of k subarrays with length at least m. The video can be a bit long. Please hold on with me. We'll discuss everything again. Spoiler alerts. Now, the problem says that an array nums is given, and again, I will try to be slow. Just I have got a feedback to be slow, so let me know that if it was slow or not, or I should be more slow. Now, in this, we are given an array nums, two values k, saying I need k subarrays in this array nums, and obviously make sure that with the help of constraints, it's always possible to have k subarrays. A quick catch: every subarray should be at least of size m. That's one more case. I have to find the maximum sum of k non-overlapping subarrays as I have given, and again they have mentioned the length should be at least m. So let's start off with very basic thing that at any point in time. Usually I recommend that you are at any point in time and then ask yourself what all you can do or what all options you have. I am, let's say, at any point again, you can take this index, this as well, right? But you can take any index, any random index, just to think of that at any point in time in your life, what options you have. Okay, obviously, one option is maybe I can start a subarray. Other option is I can skip this element and maybe start something from future. Do you see that you have take, not take? As soon as you saw, okay, it's take, not take, obviously you must have start thinking of recursive knapsack kind of problem. If not, then make sure you must have solved at least these 40 questions of DP. Or again, I usually highly recommend that to solve the practice problem sheet, which covers literally more problems and more in depth. Now, why I said to study from these videos, because the way I cover DP is different than you find elsewhere. Now, let's proceed forward. So with that, you have two options. Start your actual subarray from this index I, or you can skip this element. But making sure that maksad, target should be I have to achieve my two subarrays. That is something I have to achieve. And also length is something I can take parallelly. The biggest catch about length, even if you want to take it, you can take it, right? The length is 3. So that's the biggest catch, right? It can actually tend to help you go somewhere else as well. But yeah, m is less than equal to 3. That's also a very big catch. Let's proceed forward and let's try to think that if I start, okay, skipping is very easy. To skip anything, it's very easy. But to start from here, what I will do, or how do I know? Okay, do I have to start actually, or should I continue? Because technically, you know that you have a sub array. Now, how will I know if I'm starting or if I'm continuing? For that reason, oh, I realize technically again, when I mention I will start, because I was at the very start index, I could say that. But usually, if I am at a random index, it can either continue my existing subarray or I can start afresh. With that word itself, I realized that how would I even know that it is starting? So I will have to take another variable, either it is has started as a variable or can extend. Both are saying that has started, which means it has already started or not, or can extend. Can I extend this further or not? Both of them represent the same thing, that the array has already started and you can extend it. But as you can simply see in the very beginning phase, we were saying that okay, array has not started yet. So this is okay. I can say my can extend value is 0. Then also I realize that my remaining is what? Remaining number of subarrays which I have to build. Elsewise, it is not good if I will not build, because they have mentioned the same thing, that you have to return maximum sum of k non-overlapping subarrays. So I have to take or make those k non-overlapping subarrays. Now let's continue with the same observation. Can extend is 0. It means that the subarray has not started yet and I should continue or I should start fresh. So I will take this specific subarray. But again, when I take it, there was a very fixed condition. The length should be at least m. Now, with that length m, you can go in multiple ways. Why I say multiple ways is that you can maintain the number of elements taken in the current subarray, and that element taken, you can have one more state by saying m. So you will have index I, you will have a remaining number of k's, you will have can extend. You can have one more state of m. But obviously you see that four states can become a bit complicated in terms of, for you to solve it. Even if, again I'm saying, it is solvable. You can have one more state of m which you can extend forwards. But if we look at very naively, we'll understand that the only requirement was whatever length I am taking up, which means whenever I am starting any subarray, I should always take a length of m. So I will do one thing, no matter what, if I am starting afresh, I will take that m length for sure, which means if I am starting from index I will take the length of 2, because again in this case m was 2. So I will take it no matter what. If again, although you might ask, Aryan, you were saying it is more than equal to 2, so I can take more as well. Yes, you can take, but 2 is at least bare minimum which you have to take, and that's the reason I will take the summation of two elements starting from index I. Can you see something here which maybe you can optimize in future? Yes, one is range sum of m elements. Aryan, but it is only 3 elements, right? I can take a for loop as well. Yes, you are absolutely correct. You can take a for loop as well, because it doesn't matter. But still, a very small optimization can be using a prefix sum to find a range sum. Make sense? Okay, let's proceed forward. Now, with that, I will say, okay, as I have started and I have taken the current sum, which is the sum of these two elements, and then I will ask my recursion to solve for future. What is the future? Future is starting from the next index. Next index is I plus m. Now, because I have already taken one subarray, so my remaining is reduced by 1. So earlier if my remaining was 2, now it will be reduced by 1 and will become 1. But now the biggest question is, what is can extend? Are you saying that you will start a fresh subarray from here? No. Why no? Because I mentioned that m can be extended forward. I can have more than m elements for that subarray itself. So I will say that can extend is yes. I can still extend the existing, although I have taken this sum, but still I can extend the specific subarray, not necessarily end right now. So this will say the array has started and you can extend it in future. Okay, this is one possible option. When I saw that in the very beginning, when can extend was 0, you saw that you taking or you're starting a fresh subarray. What was the other case? Other case was very simple. Just skip things. Okay, I will simply go on to the next index. I will skip the ith index. So what I will do? No summation added, nothing added. Just go on to the I plus 1, which is the next index, and then remaining remains as is, because still your target is to take 2 subarrays. Now the can extend, this will also remain as is. What is as is? As is as in, it will also remain 0. It will also remain 0. Now you handled two cases or two options, but these options were something specific to when you were starting fresh. But obviously, you know that what if you're not starting fresh? Let's see that case as well. So we'll continue the previous case when we will actually move forward in my recursion, which means that I'm not starting fresh, I'm continuing now. Again, as I'm continuing now, I will have again two options. Either I will continue to involve or to incorporate the upcoming elements, or I can stop that continuation and again start fresh. Now you might ask, Aryan, what is the difference between this thing, what you have done, right? This thing, what you have done, starting fresh, next words here, versus this thing, what you are saying. I will tell you exactly what all or how all these are different from each other. But let's continue with extending your existing array, which means taking it. What I mean by taking it? Taking it is taking the current number. So I will take the nums of I, which is the current number. You might ask, Aryan, but you are extending, right? Why you are not taking the previous one? No, previous ones are already taken as the current sum. They are already added. So now, as the extension task, you will just incorporate the current element and then you will ask a recursion, bro, go and try for index I plus 1. Remaining will remain as is. Again, the remaining will be one subarray I have to again take in future, and then extend will also remain as is, which means still I have the possibility to extend it more in future. Now, what was the other task? Other task was no, I will not extend it, I will start fresh. What it means? It means that simply from this index I can start fresh. Now, one way is I will copy the exact same code as what I did here. That is one way. Or other ways, just tell this portion when you have reached at this index, just tell him, bro, just go and try for what you saw above, which means starting fresh said indexing from I, remaining remain as is, but can extend become 0. So because of this line, again, make sure people get confused in this I thing and say, Aryan, it is I itself, it remains same. No, it remains same, but it was in can extend, yes, but now it is going on to the above section of can extend false, which means starting fresh. So it is coming on to the starting fresh section. Now, this is the entire crux of everything what you could want. Now, you might ask, Aryan, is there anything else which is remaining? Obviously not. Why not? Because I have considered taking M at least, right? I have considered going on to all the indexes and choosing or not choosing, right? I have considered remaining, which means I will consider this as a base case that I have covered all of my specific subarrays. And can extend is already I have discussed as two cases here. And that's your ultimate example, or I can say what you have to write. Now, you will see again, this is exactly what you have to do as well. Now, I highly recommend please go and write the code, but no worries, I'll still share it. Now, as I mentioned you that for can extend, I had two options, right? Again, make sure that either you will find the notes on the website as well. But any which ways, make sure that you have this thing visible. As I mentioned, again, I'll show you that for can extend as true, you have two options, right? I'll show you two options, those again. One option was taking the nums of I and then I plus 1 with the can extend as yes. Other option was nothing plus I remaining and the can extend as 0. So same thing, taking nums of I and then I plus 1 remaining as is, can extend as yes. Same way, other option was taking nothing, then index same index, but can extend as false. Okay, so these two you have covered, right? Now, other was, as I mentioned, if I cannot extend, no worries. If you cannot extend, then you have two options. You will take a subarray. Again, as you can see, you can take a subarray sum, which is a prefix sum, which I have taken. Again, if you don't know what prefix sum is, I'll highly recommend come here. Either you can come to crash course as well. There as well, you can find the very basic prefix sums that also you can find here. Or else, I'm hoping that you know prefix sums. With that, you can take the prefix sums, or else you can run a loop as well. That's totally up to you. Now, with that, you will see that I just took, okay, I can take m elements at least. If yes, I will take the prefix sum because I have done the pre-computation here. As you can see, I've done a simple pre-computation here. And then I just asked with the current sum, go and try for the next index, which is I plus m. Remaining will decrease because I have now taken one of the subarrays and I can still extend, which means it is started and I can extend it further. Okay, what was the other case? Other case, as you know, was that one case was this one. Other case was that, okay, skip it. Go to the next index, remaining as is, and can extend obviously will be false. So, other case was go to the next index, remaining, and then can extend is false. Again, same thing. Now, you see that this piece of code is done. This piece of code is done. Now come on to the actual base case. Again, simple base case, in general, normal base case is that if you have reached the very end of the matrix, make sure that your remaining should have reached the 0, which means you have taken all the remaining, all the k subarrays you have taken. If you have not taken k subarrays, you are screwed up. You have to take the all k subarrays, and that too should be non-overlapping. Non-overlapping is covered here, but covering all case subarrays should be covered in this specific base case. that if it is covering all the specific, all k subarrays are being covered, simply return 0. Why I'm returning 0? Because the array has ended and this was already computing the sum whenever it needed any sum. So now your task is just to add something which will not impact the current sum. But if the things are invalid, add something which will decrease the sum so badly that obviously you want to maximize it. You want to maximize the sum. So if it is invalid, then make sure that you pass or you add something which decreases the sum very badly, that it will become an invalid case. That is our base case, and this is a simple memoization case. And as you can also see, a simple memo case here. Now, there's a one small thing which you might argue, Aryan, why is this line written here? Can't I write this line here? No, you cannot. Why? Because when you can, like if you can extend, great. If you cannot extend, okay, you mentioned that if it is remaining as 0, then return 0. That makes sense as well, right? Because if you have any array and I ask you that you have to take two subarrays. You have made one subarray. You have made also another subarray, and that another one has ended, which means you cannot extend it. If you cannot extend it, you have already taken two, which means you cannot take any further in future. That is the reason it is good to return 0. But why I cannot write this condition above is because if this is not complete, even if my remaining number of subarrays are 0, still I can extend it. Thus, even if the remaining is 0, still I can extend it and still my answer will change. And that is the reason I need to make sure that this condition should only come up inside my when the can extend is false. And that's how you can simply solve this answer. Again, code and everything will be available on the website, and on all these talks. Now, one thing, okay, what's the time complexity for this? Obviously you can see that indexes will go up till n. This is the remaining, which is k, and again k in the question is given n by m. M is from 1 to 3, so it can be, worst case will be n by 1, which is n itself, and can extend is nothing but true or false, so 2. So this will be the corresponding time complexity n into 2. Obviously, if you will run a loop for taking the summation, it will be into 3, right? But we have used prefix sum pre-computation, so this is a time complexity, which is n into k into n, 2. Again, as I mentioned, that k here in this case is n itself in worst case. Now, obviously, you will see the space itself is same. Now, there's a high chance that for people who write the same code, although this code right now is not giving TLE, which I have shown you, but still it has a very high runtime. One thing, again, one possible explanation because of this, why this could happen. Again, if you use a vector, you might get a TLE. So I used a simple array where all it is, inside memory, it takes adjacent space, adjacent locations. So even if you do any modifications on top of it, there's a high chance you might get TLE. And that has happened with many folks. Again, which indicates that the time constraints are very tightly, like very tight there. Although technically it should pass, but still because of recursive approaches, there is a very high chance of hitting the same thing again and again. And that is the reason recursive tend to be a bit more in time rather than the bottom-up approaches, but still on paper the time complexity is same of both recursive and top-down and bottom-up approaches. But still, as I mentioned, that if you write the exact same code, you might get a AC, but still you might see runtime is very high, around 2000 milliseconds. But obviously, when I wrote as a vector, it gave me TLE. I used it as a normal thing, a simple static or even simple use an array, you will get accepted. Now, can you improvise it? As in, like, not necessarily improvisation. This is actually perfect and should actually solve in an actual interview. But still, if you are still facing that TLE, obviously, just write this code and then convert it to a bottom-up code. Now, again, I am not the ones who convert the bottom-up code by making the matrix and stuff. This is kind of what I say BS thing. Why I say this? People teach it by like this, making matrix and stuff, but it is impossible. What I always recommend is, if the bottom up is complex, make the top down and then convert to bottom up. And the benefit for that is that bottom up can be improvised to bottom up optimized. If you don't know what that is, make sure there are literally a lot of problems which we have discussed on bottom up optimized approaches. But in general, bottom up is strictly n into n into 2, both in time and space. And that is the reason it will always give you AC. And if you will write the bottom up code also, you will get around 250 milliseconds, which is much lesser in time rather than the top down code. But you don't need to know bottom up. It's exactly same, you will see. Okay, let's see how we will write. The left side represents the bottom up code and right side represents the same top down code which we saw above. I will use the exact same code to write the bottom up code. Now, again, this is my strategy of writing the corresponding bottom up code. People teach by matrix and stuff. Okay, good for them, but I don't do by that. Now, same thing. Firstly, I will maintain a prefix sum. Although, as I said, you can run a 3 times for loop as well, a for loop having a length of 3. That is also okay. But again, if you can optimize it, why not? Now comes that how will I initialize it? As simple as that. If you see on the top down code, we said that the index has reached end. Then if the remaining is 0, then it is 0, else it is infinity. So I said that if I have reached the end, right? If my index has reached end, then whatever r is, I don't care. It is actually my base case. It is actually my base case. But it also says that whatever your r is, if the remaining r is 0, then okay, it is a 0. Your dp value is 0. Else it is negative infinity. So I did the same thing. If my r is 0, then it is 0. Else it is negative infinity. This is the exact same base case as what we saw in this line. Now, let's proceed with converting remaining piece of code. Obviously, we know the remaining piece of code. The states in our DP or in our previous approach was having an index, having a remaining, having can extend. These were the state. Now can extend was only true or false, so I can handle it separately as well. But the main crux is index and remaining. So the base question is, how will I move my index? Will I move my index from 0 to n minus 1? How will I move my remaining? Will I move my remaining from 0 to k minus 1? How? That's a question. And that's the biggest question which comes in mind. But you know that obviously in the very end, you can return 0, k 0. What is that? Obviously in the end, I can return 0, k 0. Oh, you see that everything is same. Okay, everything is exactly same. Now, the biggest task is how will I proceed? So you will see I've written index goes from n minus 1 to 0, while remaining goes from 0 to k. But how did that happen? Simple. If you look at your recursive code, you will realize if you were at index I, or if you were at index, you needed index plus 1, which means that if I want to compute dp of index, I don't care whatever is after that, whatever state is after that, but I should be knowing dp of index plus 1 for that. So which means that I have to start computing index from the opposite order, so that whenever I am computing for dp of index, I should already have an information of dp of index plus 1. Okay, what about the remaining? Remaining says, okay, for remaining, I need to know the remaining minus 1. Oh, which means that for dp of anything and then remaining, I need to know somehow dp of anything and then remaining minus 1. Which means that for remaining, I should go in the smallest to larger order. For remaining, I need the previous value. For index, I need the next value. It is the reason my index went from n minus 1 to 0, while my remaining went from 0 to k. And again, that's the reason. You don't have to get confused on anything. It is exactly same as what you wanted there. Okay. Now let's proceed forward. If you remember, earlier we used to take can extend. But then I told you that can extend technically we are handling in a bottom-up code by saying 0 or 1. Right? In the DP state, we have I, we have remaining, and then we have 0 or 1. This represents can extend for us. So obviously this is, as you can see, we're handling everywhere. 0, 1, 0, 1. Every time we are handling it. The biggest thing is, which you could take as an edge case as well, that for any remaining, you are handling remaining minus 1 as well, right? That's one thing. So for that, again, you can handle it as an if else also in this case, but that's one thing which you can do, that okay, if the remaining is 0, which means remaining minus 1 will not happen. In that case, I took the same thing. I said that okay, bro, just let me know that okay, if the remaining is 0, again, make sure that you are viewing all this on a laptop, on a or maybe phone. You can zoom it, but I have to make sure that I'm explaining both of the things simultaneously. So I have to make it a bit more small, and it might actually impact your viewing experience. Now coming on back, I realized, okay, if the remaining is 0, now the biggest challenge here is that I can have two possibilities. If I can extend or if I don't extend. If I don't extend, if the remaining is 0, obviously the answer is 0. Obviously the answer is 0. But it is, if I don't extend, it is 0. So, oh, I am sorted. But if I extend it, then I have to take in consideration these two cases. So what is these two cases? First case says add the index, go and try for the higher index, remaining and 1. So I did the same thing. Add the value, index plus 1, remaining 1. This is, okay, yeah, this is exactly what I did here. Nums of index, nums of index plus I plus 1, remaining 1. I plus 1, remaining 1. Other case was do nothing, add nothing, I remaining 0. Do nothing, I remaining 0. And that's how I simply incorporated both these two inside this line. Cool. Now this is done, which means can extend is done and cannot extend is also done. Okay, these two are done. Let's erase this. Let's simply erase this. Let's proceed forward. Obviously, now I'm in the else case, which means I have now remaining more than 1, which means I now can simply go on in this portion. Entirely, I can go on in this portion. For this portion, you see, there are two things. I need to compute the current sum. I need to compute that as well, best thing. So obviously I have two options. Either I can take this option or I can take this option, whatever gives me maximum. That's my case. For that, obviously, I know that I will try the same thing. I checked that if I can take an array of size m, I will take that, which means I will find the current sum. This is the current sum. This is the current sum. Exactly. Then I will say that in I plus m remaining minus 1, 1. I plus m remaining minus 1, 1. Cool. Okay. This portion is also done. This portion is also done. What is remaining? Remaining is this thing, which is I plus 1 remaining in 0. I did the same thing. I said I plus 1 remaining 0 is being maximized against what? Against the option 2, which I will put up here. Okay, so this is also done. This is also done. What is remaining? Remaining is now, what if I can extend? Because see, so far you were doing for 0, but now you have to do for 1 as well. 1 says can extend, can extend. So again, the same thing as I did above, exact same thing I will do below. That nums of index plus dp of index plus 1 remaining and 1. Same way, dp of I remaining and 0. And that's how I can simply, with the help of simple human brain of pattern matching, I can convert my top down to a bottom up code. And with that, you will see the runtime will be very less. Again, no brains applied here. Logically, it is exactly same. It's just that how I mapped my top down to bottom up code. And with that, time is still same. Space is still same. But still, it will exactly now run for n into n into 2. And space is also exactly n into n into 2. And that's how I can get rid of TLE. Again, if you are getting a TLE, obviously you might get TLE if you implement it. But yeah, this will never give you TLE. Now, there's one more thing which I will not cover technically, but there's one more thing. Obviously, you will realize that for any index, again, this is an approach which we have discussed quite a lot in many videos. And again, all these names, numbers are listed here as well. And also, if you would have practiced the practice problem sheet, it would have been covered here as well. But the entire essence is that, as you can see, for I only need I plus 1. For I only need, I plus 1. The only catch is for for my option, I need I plus m as well. And I know m is limited. M is limited. So I can try for m possible states next. This is kind of same as prev dp, which you must have seen in the old videos. Prev dp, how we used to optimize the bottom up approach, optimize in terms of space. So this is a code which I will link in description. If you want, you can have a look. But this will help me. Time will still remain same, but the space, rather than having a n now, will go away, and I will have k into 2 into m. And m in this case is 3. And that's how I will be able to optimize my space. Again, time will still remain same, but the space can be optimized. I hope you guys got it. Bye bye. Take care. Please make sure that we hit the like target of 100 likes. It will be very beneficial to make these videos for contest after work. Bye bye.